Hello everyone, thank you for coming. My name is Pietro, this is Sebastiano, and we are data scientists at Agile Lab. For those of you who don't know, Agile Lab is an Italian software consulting firm that specializes in data engineering, data science, and solving data problems for organizations. We wanted today to present to you this use case that we have been working on, which is how we have architected a scalable multi-modal video search solution. So just by show of hands, I wanted to ask you how many of you have worked in the past on, with video data or large amounts of video data? Well, I think no one, but, oh yes, we have one, so it's going to be very relatable to you. So the problem today that we have is that we produce an enormous amount of video data and always is increasing. And more often than not, we want to be able to perform some sort of semantic search over this data. But it's very challenging because the computation, it's limited, and processing this data and performing semantic search, it's unfeasible at a large scale. And so our objective is to perform semantic search over like a large video corpora. And we want to be able to do this in a multimodal way, so meaning taking in both text and images. And we want it to be very efficient, both in the models and the pipelines, because of the restriction that I mentioned. Some use cases for this are broadcasting archives, investigative analysis, and compliance and safety. And now we wanted to present to you a live demo of the Deckard platform. So this is the user interface. On the left you have some the data set with various videos that you have uploaded of whatever is your use case. And then what you can do, you can go on to ask in natural language something like, find me a man with a red sweatshirt in this case. And what it's going to do, it's going to show you example of what it has found matching with your query. And you can click on those examples and see the point in the video where he appears. There is many different points in the video, even if the video is very long. And you can go back to the video, and also another thing that you can do, you can query by selecting an image as opposed to just using text. And even with just that, you can find the same thing within the same video where this man with the red sweatshirt appear, you're going to find it. And so the pipeline has 3 steps. The first step is about offline preprocessing, and it's also divided in 2 sub-steps. The second step is about real-time retrieval and search, and the first step is about AI agent assistant and video intelligence. To go a little bit more in detail on the first step, we perform different video processing tasks. We do video ingestion and frame sampling, object detection and tracking, keyframe selection, and crop extraction with metadata. So starting with the video ingestion, the first thing, because we want to avoid processing and saving all of the frames, because in a video that might be high frame rate video, there is a lot of redundancy in the data of frames that are close together. So our solution is to simply drop every nth frame and do subsampling. Then for the object detection and tracking, we use 2 models. We use the YOLO V11 model for object detection, and we use the bot sort algorithm for tracking this object, assigning an ID of this object and tracking it throughout the video. We perform some tests on the YOLO model using different model sizes, 2 different model sizes, and varying batch size. We found that it has this U-shaped relationship. excuse me, this U-shaped relationship between batch size and the throughput of the frame, meaning if your batch size is too small or too big, you hinder the throughput. Then for keyframe selection, so we want to, once we have these objects that we have detected and are tracking, we want to filter out edge cases and prioritize high quality detection to avoid storage explosion. In the first case, we filter out edge cases by calculating a score based on a weighted combination of the confidence of the detection and whether or not, a flag that describes whether or not the tracked object was next to the actual edge of the frame. And based on a threshold, we decide whether we want to keep this example or not. For prioritize high quality detection, we sorry. To prioritize high quality detection, we simply took these images, we compressed them in an 8x8 image, then we calculate a hash 64-bit vector so that we can calculate Hamming distance between these vector as a proxy to how similar the original images are. And of course, we want to keep images that are different between each other so that we maintain the most useful information as possible. And we drop images that are close together.
Okay, so I'm not here just for playing buttons on the demo. I'm here also to tell you something about semantic vector store. So the idea in this case is that after the previous step, you have a series of images. Those images, you want to turn them into something that can be searched. So basically a vector. So I don't know how many of you are familiar with models like Siglip or Siglip2, so I will go through a brief explanation about them. So the idea is that there are some AI models that are able to turn an input like an image or a text into a vector. Those are called embedders or encoders. And while doing that, they are able to maintain some special characteristics. So for example, these models like Siglip, for example, are able to turn both vectors, both images and text into a vector. And the specialty here is that if the text that we are giving as an input is the description of that image, then the vector resulting will end up more or less in the same place. So let me give you an example. Suppose that you have a series of images of dogs and a series of descriptions of dogs, and you embed them using one of these models, then you will end up in the same area into a vector space. And you can do that not only for images and text, but also for faces. For example, ArcFace, which is another model that we are using, is able to turn a face into a vector. So we tried this model and they were pretty good, but at the same time we wanted to go further. So we decided to fine-tune these models. How do you fine-tune? Basically, you take additional input, so pairs of images and text, you put them together and you train the model on top of this additional data that you have. And as you can see here, by fine-tuning Siglip2, we were able to match and even pass the state of the art. In addition to that, I wanted to add some information regarding the kind of dataset that we have used, because we have used the publicly available dataset, but also this OpenSet ReID, which is a dataset made by images and text descriptions that are generated using Gemini. This is very interesting because it allows you to turn every kind of data set of images that you have into something that can be used to train this kind of models. So as I said, you have inputs like images and text, and you turn them into a vector. But if you want to see those vectors, that's difficult, basically, because you have vectors with more than 1,000 dimensions, so we cannot imagine them, but at least we can represent them using techniques like PCA, so dimensionality reduction. So in this case, all these points here are points belonging to that dataset that we have seen before, so images of people, basically, and you can already see that PCA is able to find, let's say, 2 groups. Can you guess what are those groups? You know, just a question. Anyone? 10 points. So how can we demonstrate that? We said that basically you can embed not only images but also text. So if you use some text and you put them into this vector space, you will see that on one side you have a woman, a girl, on the other side you have a man, a boy, and then if you also plot all the images on top of those points in space, you will see that actually those are divided according to what we have said before. So this is just a way to understand how images and text can be turned into vectors. But after you have the vectors, then you need a way to store and then search those vectors. So we decided to use Qdrant, pretty easy, and we attached to those vectors that we have created a lot of information regarding the object, the timestamp, location, bounding boxes, basically everything that you might need for this kind of application. Once you have all this data set, then you can basically go back to the front end that we have seen before. So you can start your search. Searching, again, is pretty straightforward now that you have your vectors. So what you need to do is you take your input, you turn them into vectors. So basically, you select the image, as we have seen before, or you write some text. You send the text to the backend. The backend will encode that into a vector, and then we will search for the vectors that are closer to this one. And then you can also do like kind of crazy stuff, basically, because you can mix text and images, or search just images, or search first the face and then the image, or vice versa. The combinations are limitless. Something that I wanted to underline here is that the algorithm that is behind this kind of research of search is the hierarchical navigable small word algorithm that it's, or let's say, a standard for this kind of application, and it's able to find in a relatively small time exactly the vectors that you want. So it's very good for this kind of applications. And now let's move back to agents.
So the last step of the pipeline is about using an LLM agent, specifically a multi-modal vision-enabled VLM to provide to the user the ability to answer questions about the video. And it does this after having processed the video in a certain way that we'll soon see. So the first thing is we use 2 models. Mainly the first model is VN3, 8 billion parameters model. We use that for reasoning as an orchestrator. You can think of that as the brain of the agent. And then we use a multi-modal VN 2.57 billion parameter model that has vision capabilities and can see and interpret pieces of the video. And it has auto-summarization abilities and can also find relevant video moments, and we will see which tool corresponds to that in a second. So before you can chat with the agent, there is a pre-processing step to calculate certain things that are used by the agent. When you upload a video, the first thing is that it's uploaded to an object storage so that the agent knows where to go look for it. Then it gets chunked into video segments. And with these chunks, we calculate descriptions of each chunk using a language model, still the VN vision model, and we store this description in a Postgres database. Also, with the same chunks, we embed them into vectors, and we store this vector in the Qdrant database. Additionally, we also extract metadata from the video and store that as well in the same Postgres database. So to go over a little bit of how the main framework works, it's a very typical agentic framework where the orchestrator receives a query by the user, and then it can decide to use any tool it wants. Then after that, it reasons about whether or not it has collected enough information from the usage of the tools. If not, it uses, again, other tools, and this loop continues until it decided, okay, I have enough information, here's the response. The tools in questions are 3. The first one, get video descriptions tool, simply fetches the video descriptions in the Postgres database and returns them as the response of the tool. The second tool is a search video segment where it takes an input query and queries the current database for to search for a segment that matches the query. This tool, the output of this tool is simply the indexes of the frames of that matched segment. It's not the video itself. And then finally, we have the query visual model, which is a tool that you can give it, or the orchestrator gives it an input query and the frame range, and simply gives this and queries the when vision model for a response that is given back to the orchestrator. Usually, the way these tools are used, we have seen, is that it's going to get the descriptions. If it can answer from that, it's going to give the answer. If not, usually the other 2 tools are used together. So you get the indexes of the frame of interest, and then you query the visual model. And the last thing I wanted to mention about this is that it has obviously some limitation when it comes to the pre-processing part for using that with very long videos. Yeah. Yeah. So we are gonna also see a little video demo of this. So as with before, we wanted to search for a man with a red sweatshirt in this video. So we asked the agent, and we see that it gives a long response where it has found the right answer. The other capability of this, let's say that's specific kind of to the when model, is that it's going to give you a reasoning for what it does. So you'll see it has a first response, that's its reasoning, and this is specific to the when model. All other model can do this as well, though, and it tells you which tools it's going to use and why. So this is quite good for interpretability. And then it gives you if the loop continues, it gives you again the reasoning for every time it decides to continue the loop. But in the end, it's going to give you the response of what you asked.
Okay, so we have discussed about how we implemented this. So we have discussed about the pipeline, basically, but this was a POC that we have developed, basically, to understand how feasible is this kind of approach and how it scales. So we decided to run some iterations in order to understand better the path to efficiency. So how do you start from a POC to something that can be deployed in production? So first of all, as we said, the first problem that you have to solve is how you ingest video and how you ingest frames into your system. So the basic approach that you may think of is using basically FFmpeg. So you go frame by frame, you turn them into a tensor, and you basically use that. However, there are faster solutions that can be used in order to avoid some passages. So for example, suppose that you have a GPU that has hardware that is able to decode videos. So it's better for you or to use a specific version of FFmpeg that is compiled to do that, or otherwise you can use this library by NVIDIA that gives you access to this kind of hardware. In addition to that, this kind of flag that you see here, it's also very important because by using device memory only, you allow this library to store the frames directly on the GPU without moving those frames from the GPU to the CPU. We will see that this is a recurrent problem in the next steps because what you want to do is to leave as much as possible on the GPU. And in order to do that, there are some libraries that you can actually use. One of them is DLPack. We will see that later. That basically, I'll give you a few words now, gives you a way to move tensors from one place, from one framework to another without copying data, which is extremely fast. So we have seen before that in our pipeline, we have different steps: the video decoding, the detections of the objects, video tracking, keyframe selections, crop embedding, face embedding, and then store the embeddings. If you see this image here, you will see that data is moving a lot. So you move from the CPU to the GPU, back to the CPU, and then back to the GPU, you name it. So this is basically very, very slow. So how do you make this faster? As I said before, first of all, video decoding. If you decode videos on your GPU, basically you are reducing by a lot the amount of time that you spend moving tensors because the tensors that you are going to use are already there. So one way of doing that is using this library, for example. Then detection. We worked a lot on detection, first of all, because most of the libraries that you may use, so for example, Ultralytics, has some pre-processing and post-processing steps connected to that detection part. And it happens that pre-processing is done on the CPU, then the tensor is sent to the GPU, back to the CPU, and then you have post-processing. So in order to avoid this kind of back and forth, we decided to turn that pre-processing step and post-processing step into PyTorch code, basically, so that it can run also on the GPU directly without moving anything. Then video tracking and keyframe selections. In this case, we had to work quite a lot in order to turn the video tracking, so basically when you have all the different bounding boxes from the frames, you want to keep the IDs equal from one frame to another. Usually you do that by using a Kalman filter, and we had to implement that in PyTorch in order to, again, not moving data around. Same for the keyframe selection. You have seen in the slide before, when we compute the image hash, we do that using PyTorch. And finally, we have the models that are already on the GPU, so not much work there. But still, whenever you are working with this kind of models, you also want to use your hardware as much as possible. So for example, if you can turn those models into TensorRT models, that will help a lot, increase performances, and also provide you a better experience. By doing this, in addition to do that, you can also, as I said, use DLPack to avoid copying frames from one framework to another. So in this case, zero copy is super fast, and you are able to, by combining all these steps, obtain very high throughput. So basically, we had a 10-pair improve by just moving everything where it belongs. Few words on DLPack. So this is a library that is used for tensor interoperability. So basically what you have here is just a pointer to a memory location in space. What you have basically is one way to move those tensors from one point to another. Because as we have seen before, whenever you have a frame, you take the frame, you put that on the GPU, then you have to select some bounding boxes. So basically, you are creating additional frames. You can avoid that by just providing the exact locations in memory and then pass that into the next steps. In this way, everything is super fast and you don't have to make copies. Also, this kind of library supports frameworks like PyTorch, NumPy, TensorFlow, so it's super useful. Some final takeaways. I just wanted to tell that by presenting this POC, we have demonstrated that it's possible to process large video dataset with by using technologies that are available nowadays. And also, it's easier to process this kind of data when you have a lot of pre-processing on the frames. So when you are able to extract only the images that you actually need and embed only the informations that you actually want in your dataset. Then, as I said, for efficiency, it's extremely important to avoid CPU and GPU round trips because you want everything to be on the GPU. And then with the last part, with the agentic model, we have started working on how large language models are able to process this kind of data set. As we said, it's very difficult sometimes because you need a lot of memory, especially if you want to keep as many frames as possible inside the VLLM. But sometimes it's just a matter of deciding where to put the different information on databases or in the memory, and by using this kind of distributed approach allows the video model to use the right tools in the right moment. Then there are lots of fine-tunings that can be done. So for example, whenever you do a kind of this kind of approach, you need to test it on the hardware that you have. So based on the dimension of the GPU that you have, the memory constraint that you have, different parameters, different batch sizes might give you better or worse results. So just play with parameters. And again, zero copy, it's the best way to move along. So before thank you, I want to thank the team that worked on this project. So Irene, Rashid, Antonino, David, Fabrizio, Diego, and also Pietro and myself. And thank you all again.
Thanks a lot. Any questions?
Thank you. Really interesting talk indeed. You seem to have used a lot of open source stuff, so I'm wondering if you have tested the quality of the embeddings from the other like commercial offerings such as OpenAI's or Amazon's, etc.
Okay, so we have not tested it because we just used, right now at least, this kind of solutions for writing down a small POC. So this is not just a product. It's something that we wanted to use to test the different possibilities that are out there. So something that we are probably going to do is also testing different models and see how it works. However, SIGLIP2, for example, provides you performances once you fine-tune that are almost state-of-the-art. So the last slide that the slide that was shown before, so this one, basically. So this Mars project is a paper that has been published last year, basically, that is state-of-the-art in array identification. So given a text, return the exact image belonging to that text. And by just doing fine-tuning on SIGLIP2, we were able to get to very similar performances.
Hi, thank you for the very nice talk. Have you been collecting and verifying user input and responses? If that makes any sense? Thank you.
So we don't, as you said, we don't have it in production yet. We have it as to show as a POC, so there isn't a lot of production-ready data that we can collect, but we tested mainly manually and a little bit with MLflow for checking differences in, for example, the vision model, but yeah, I'm not sure if I answered the.
Other questions? Don't be shy. We have as much time as you want. This is the last talk. If not, there's one extra. Okay, he has more questions. Okay, let's go.
So one other thing I was wondering about was that when besides working on different embeddings and the performance of them, I was wondering because you spend a lot of time talking about how to make it more efficient, right? So how to like use zero copy and reduce the transfer between CPU, GPU, etc. But I'm just wondering, like, because for some use cases, when, for example, you would have like batch processing, so this wouldn't be actually needed. So you could just basically just not do any of these performance improvements. So I'm wondering what is, like, if you could make it like tangible in terms of like, if we wanted to build such a system, like what would you advise? So when would we need definitely to do these performance improvements, and like, and when would we just, you know, wouldn't need to care about it, so it could just work? I don't know if this makes sense, the question.
So you're talking about like which is our bottleneck?
Yeah, so which use cases, like batch, real time, or like which specific use cases when you saw that, okay, it's an absolute requirement to optimize performance, and when it's like, you know, you can just implement the plain, you know, what you would just do the first shot and then it would just work, it would be good enough.
Yeah, correct. So it's a matter of deciding which are like the thresholds that you want, the results that you want to achieve. So for example, in this particular project, we started with, okay, we are going to have, for example, 10 video streams in real time, full HD. Is that possible to process all that data using just a single A100 GPU? Yes, no, basically. So we started from this perspective, and then we started moving, okay, first thing we can do, we remove some frames, then we optimize on the GPU, then we optimize on the model. Something that I have not said, but you can actually do that. Instead of using the SIGLIP2 with lots of parameters, you can use a smaller model that is fine-tuned, for example. And the results we have done some tests on that and are pretty similar to what you can get even with bigger models. So you're losing something, but it depends on the kind of trade-off that you want to do. But basically, the idea is that you fix something that you want to achieve, and then you tune all the parameters.
We can thank the speaker again.